I used to wonder why it is written that the flux is linking the coil and not moving through the coil. It is due to the reason that flux never moves. We say that the flux is linking the coil if its direction is perpendicular to the plane of the coil. We say that the flux is not linking the coil if its direction is in the plane of the coil. The flux linking the coil is maximum, but d phi by dt is equal to 0. Hence, EMF induced in a coil is 0. When the poles are rotated anti-clockwise by 90 degrees, flux linking the coil is 0, but the rate of change of the flux is maximum. Hence, induced EMF is maximum. When the poles are further rotated by 90 degrees, EMF induced in the coil again becomes 0. Let us examine the induced current with various types of load. A pure inductive load is connected to a generator. Since an inductive load current lacks voltage by 90 degrees, maximum current is induced in a coil when the poles are ahead of a coil by 90 degrees. Mostly load is inductive and resistive. Let the phase angle is phi. The maximum current is induced in a coil when poles are ahead by phi plus delta. Delta is a load angle between the induced EMF and terminal voltage. In case of a resistive load, current is in phase with voltage. Maximum current is induced in a coil when poles are ahead by load angle delta. Capacitive load comes when a generator is lightly loaded. It is due to the capacitive current in transmission lines. When a capacitive and a resistive load is connected to the generator, maximum current is induced in a coil when poles are behind the coil. When a pure capacitive load is connected to the generator, maximum current is induced when poles are behind by 90 degrees. When a load is connected to the generator, armature flux is produced due to armature current. It opposes or aids the main flux to produce a resultant flux. Change of resultant flux is shown when load changes from pure inductive to inductive and resistive. Change of resultant flux when load changes from inductive and resistive to pure resistive is shown. Change of resultant flux when load changes from pure resistive to resistive and capacitive is shown. Change of resultant flux when load changes from resistive and capacitive to pure capacitive is shown. Induced EMF E, as per Faraday's second law of electromagnetic induction, is equal to minus n d phi by dt is equals to minus n d phi m sine omega t by dt is equals to minus n phi m d sine omega t by dt is equals to minus n phi m omega cos omega t is equals to minus n phi m omega sine 90 minus omega t is equals to n phi m omega sine omega t minus 90 degree. Induced EMF terminal voltage and reactance drop lags main flux, resultant flux and armature flux respectively by 90 degree. When load increases, load current and armature flux increases, resultant flux decreases. Since the terminal voltage is proportional to the rate of change of the resultant flux, it also decreases. When a load changes from inductive and resistive to pure resistive, resultant flux increases and terminal voltage increases. In this video, we have seen the change in phasor diagram of flux and voltage with change in load and type of load. As the load increases, resultant flux decreases, resulting in the decrease in the terminal voltage. As the load changes from inductive to capacitive, resultant flux increases, resulting in the increase in the terminal voltage.